So today, I'm going to tell you about my work on helping systems developers better understand the performance of their code before it is deployed in production. And this is joint work with my advisors at EPFL, Katerina, Argyraki, and Candea. So first and foremost, let me clarify what I mean by better understand performance. With this phrase, I'm referring to helping developers answer frequently asked what-if questions about the expected performance of their code, particularly for unseen and untested workloads that it might face in production. Now, developers ask themselves many performance-related questions, but in this talk, I'm going to focus on questions related to how the code interacts with the underlying hardware, specifically the CPU caches. And the reason we're going to focus on CPU caches is because, given the ever-widening gap between processor and memory speeds, how the code interacts with the cache hierarchy often critically determines performance. And this is particularly true for low-level code, such as OS kernels, network stacks, device drivers, and so on. So to give you a concrete example of the kind of questions we're trying to answer, consider a developer, Alice, who is trying to build a fast in-memory key value store, which consists of a hash table that she wrote herself and a network stack that she is using off the shelf. Now, because in such systems, the throughput is often bottlenecked by the number of last-level cache or LLC misses per request, Alice needs to know the kind of workloads that cause consistent cache misses, and then to optimize her code, needs to understand how each part of her code base uses the CPU cache. So for instance, how many cache lines does the hash table code touch per put and get request, and how many cache lines does the TCP stack touch per network connection? Unfortunately, answering these questions today using tools such as profilers and simulators is very, very hard. And the reason for this is because these tools are designed to provide visibility into the concrete workloads that the code is profiled or simulated with. And they cannot provide visibility into abstract or unseen workloads, which is what Alice wanted information about in the first place. And as a result of this, developers are forced to manually extrapolate and guess the answers to their key questions, which is not only time-consuming, but also error-prone, particularly for code they didn't write themselves, like the network stack in Alice's case. And to give you an example of just how hard these questions can be to answer, a recent patch showed how the fast path of the Linux kernel's TCP stack, which is probably some of the most heavily exercised code in the world, had been accessing 50% more cache lines than it needed to for over a decade. And this was leading to slowdowns of up to 45%. So clearly, developers like Alice need better tools. And if you take a step back, we realize that the status quo is due to a lack of performance abstraction. Specifically, Alice needs visibility into what her code does to the cache as a function of the workload. That is, how her code processes an abstract or symbolic workload. Unfortunately, the only way for her to get this information today is from the implementation itself, either by reading it, which becomes infeasible after a point, or by painstakingly profiling it with concrete workloads one at a time. And so, in this work, the question that we're asking is, can there exist an abstract to symbolic representation of the code that enables developers like Alice to efficiently reason about cache usage, so without having to delve into the code's details or having to run elaborate benchmarks? And so in answer to this question, we propose the notion of memory distillates. A memory distillate is an abstraction that retains all the information relevant to how the code accesses memory and discards everything else. So when given the same inputs as the code, the distillate is going to produce an identical trace of memory accesses, but will not, for instance, produce the correct functional outputs, because functionality is one of the many things it abstracts away. And so we use this notion of memory distillates to build CFAR, which is a tool that allows developers to efficiently reason about the cache usage of not only their own code, but also third-party code. And CFAR does this in two phases. In the first phase, it uses automated program analysis to extract the distillate from the code. And the second phase, it allows developers to query the distillate to answer their specific cache usage questions. And the key idea behind this two-phased workflow is the flexibility it provides. Because the distillate is precise, developers can use it to answer diverse questions about cache usage. I'll give you an example of this later in the talk when I show you how developers can go beyond performance analysis and also analyze security properties of their code. So I will get into the details of CFAR in the rest of the talk, but if there's one thing I want you to take away, it is that memory distillates provide a simple yet precise abstraction for reasoning about cache usage. They're precise because they contain all the information relevant to how the code accesses memory, but they're much simpler than the code itself because they discard everything else. So here's an overview of CFAR with the three key components, the distillate in the middle and the two phases. Now I'll get into the details of each of these three components, but before I do, I want to qualify the scope of CFAR by touching upon its limitation and assumptions. So as I told you, CFAR relies on automated program analysis techniques, specifically symbolic execution, to extract distillates, and is so subject to the scalability limitations of these techniques. In particular, this makes it ill-suited for multi-threaded code and code with loops without statically computable loop bounds. However, despite these limitations, I'm going to show you in our eval how CFAR still produces useful information for a wide variety of systems code. Second, CFAR cannot reason about speculative memory accesses. These accesses can perturb the state of the cache, but because they're hidden by the underlying hardware, CFAR, or really any tool, cannot reason about them. And finally, CFAR assumes that the program is not preempted during execution. CFAR does this because it is infeasible to reason about all possible programs that can run when the program in question is being preempted, and so conservatively assumes that no preemption occurred. So that said, let's go to the details of CFAR, starting with the distillate. And to do so, I will use an example, the create system call, which creates a new file, from the hyperkernel, which is a simple research kernel. While being simple, and much simpler than production kernels like Linux, the hyperkernel has very similar input-dependent access patterns. So on this slide, you see how it uses the file descriptor and the process ID to index into kernel states such as the process table and the file table. Now on this slide, you see the data cache distillate for the create sys call. Now CFAR extracts a similar distillate for the instruction cache, but I'll have to refer you to the paper for that. Now, before you try reading this, I want to emphasize that the distillate is an intermediate representation, and it's not something that developers are going to read directly. Nevertheless, there are a few things I want to emphasize. So first and foremost, the distillate of a program is another program. And the distillate is going to take in the same inputs as the program and going to maintain the same state. So for example, the distillate here takes the same inputs, such as the file name, the file type, and so on and so forth, and maintains the process table and the file table. The key difference is in what the distillate returns. So instead of computing the correct semantic or functional outputs, the distillate is going to return an ordered sequence of memory accesses. And each memory access in that sequence is a tuple consisting of a type and an address. Now the type can either be a read or a write, and the address is a symbolic expression expressed as a function of the input I and the state S. And the reason we chose this symbolic representation is because it allows the distillate to be precise. So no matter what the concrete values of I and S are, no matter how the address space is randomized or where the code is loaded in memory, the distillate will always be able to precisely replicate the exact sequence of memory addresses you get when you execute the program in question. So that was the distillate. Let me now walk you through how we extract this distillate from code. So the process of distillation in CFAR consists of 4 steps. The first step is symbolic execution, where we analyze the code to enumerate all paths through it. And when doing so, we extract 3 pieces of information for each path. First is the path constraints, that is constraints on I and S that uniquely determine the path. Second is expressions for the symbolic memory accesses. And finally, a concrete input that exercises the path in question. In the second step, CFAR replays the binary of the code with these concrete inputs. And the reason CFAR does this is to take into account parameters such as how the compiler optimizes the code, and also be able to look into features such as what memory accesses were actually accessing memory as opposed to registers. In the third step, CFAR really puts together the information extracted from the code and the binary. And so what it does is it uses debug information to collect the information extracted from the binary trace and from analyzing the source. And in the final step, CFAR translates this execution tree we have, which is at this point in time composed of SMT constraints, into the Python program or the distillate that I showed you before. So that was distillation in CFAR. And at the end of this process, we have the distillate that contains all the information relevant to how the code accesses memory. I'm now going to show you how the projection step turns this into focused and actionable answers to specific questions about cache usage. And the way we do so is by allowing developers to write simple programs that we call projectors. And these projectors are going to operate upon the distillate and compute answers to specific cache usage questions. So more specifically, a projector is a user-defined function that is going to take as input a Python list containing symbolic memory accesses and output the answer to a question about cache usage. So you have two simple examples on the slide here. If you compute the length of the list, you're going to get the number of memory accesses. And the second expression allows you to compute the number of unique 64-byte cache lines touched. Now, CFAR comes with 3 pre-provided projectors that developers can use off the shelf. The first one helps developers understand how cache usage scales as a function of the workload. The second one lets them identify the precise hit and miss profile of their code. And finally, the third one allows them to go beyond performance analysis and identify and analyze the security properties of the code and analyze whether their code has secret-dependent branches or memory accesses. Now, I won't be able to get into the details of these 3 projectors, but what I want to emphasize is that they're very easy to write. And the reason for this is that they're usually code agnostic. So they only operate on the sequence of memory accesses returned by the distillate. They don't care how this sequence of memory accesses was produced. That heavy lifting has already been performed in the distillation step. So those were the 3 steps in CFAR. I'll now quickly walk you through a few highlights from our eval. So we analyzed a wide variety of programs with CFAR. We analyzed the fast path of TCP from 4 stacks, 2 versions of the Linux stack, the X kernel bypass stack, and the LWIP stack for embedded systems. We also did 2 open source hash tables, all the syscalls from the hyperkernel, and 7 algorithms from OpenSSL. And we were really interested in 2 questions, which is, are the CFAR extracted distillates are they accurate and are they useful? So to evaluate the accuracy, we manually wrote test cases that covered approximately half the paths for each programs we analyzed. And what we did here was we measured for each path the number and the addresses of the executed instructions and the data memory accesses. And we compared these measured values to the values predicted by the distillate. And in each case, we observed 0 error. So CFAR's distillate was perfectly accurate and held irrespective of the concrete values of the input in the state and factors such as how the address space was randomized. So to evaluate utility, one of the questions we asked was the question that Alice wanted to answer at the start of the talk. So we used CFAR to analyze 4 TCP stacks, so Linux before and after the recent patch, the X kernel stack, and the LWIP stack. And what we asked it to do was predict the number of connections at which the working set of each would overflow the cache, leading to consistent LLC misses. So on the slide here, you see the predictions that CFAR gave you. So the old version of the Linux stack is the least efficient, and it increases in efficiency up to the embedded system stack. And to validate these predictions, we ran each of these 4 stacks, and we measured the latency. And you see the results on the slide here. And what I want you to notice is that for each of the 4 stacks, you start seeing a sharp increase in latency at around the point predicted by CFAR, which tells you that developers can now use CFAR to analyze code that they've probably never seen before and answer key questions about cache usage without having to write any benchmarks. So I'm going to finish by showing you an example of how CFAR also allows you to analyze security properties. And so what we did was we took the 7 algorithms from OpenSSL. These include widely used ones such as AES, SHA, RSA, etc. And we used it to analyze whether they have leakages due to branches or memory accesses. And so in doing so, we not only reproduced a known cache leakage vulnerability in RSA, but we also found a new violation of this property known as constant time in AES, which had been latent for almost 4 years since OpenSSL 1.1. Now, this violation has been acknowledged by the maintainers and is in the final stages of being merged. So to summarize, today I told you about CFAR, which is a tool that allows developers to reason efficiently about the cache usage of not only their own code, but also third-party code. And the key idea behind CFAR is this notion of a memory distillate, which provides a simple yet precise abstraction that developers can query to answer their specific usage questions about cache usage. Now, CFAR is part of a larger project at EPFL called Performance Interfaces, where we're trying to build such performance abstractions that help developers answer many more questions about their code and systems in general. And so we have a second instance of this work in tomorrow's post-lunch session. So if you liked any of the ideas presented in the talk, please do attend that talk as well. You can find more information about CFAR at the Performance Interfaces project page. Thank you for your attention, and happy to take questions.